Okay, welcome to chapter 1 in pre-calculus. We're going to start out with some very basics and then proceed to a little bit more difficult material. So if you feel like you're, bored with the first couple sections, then I would say just hang in there. It's going to get harder pretty quickly, but we do want to start with the basics because some people haven't had pre-calculus in quite a few years, or for various reasons they need a little bit of a review, and that's what these first sections will be. Okay, so to start with, we want to talk about real numbers. Real numbers, we have several different groups of real numbers. We have our natural numbers, which are also sometimes referred to as our counting numbers. And basically, when we start to count something, we start 1, 2, 3, 4, 5, and that's our natural numbers. Integers include your natural numbers, 1, 2, 3, 4, 5. It also picks up the number 0, and then it's also the negative of all of the natural numbers. Okay, it includes no decimals or fractions, just the natural numbers, 0, and the negatives of the natural numbers. Okay, rational numbers is another subset of real numbers, and rational numbers can be are constructed by taking the ratio of integers. So any rational number can be written as a fraction. Okay, so all of these are examples of rational numbers: 1/2, -3/7. So we can have negatives with rational numbers. Any whole number can be made into a fraction by putting it over 1. And most of your decimals that are either terminating or repeating are going to be able to be made into a rational number as a fraction over a fraction. Okay, we cannot divide by 0, so just keep in mind that division by 0 is undefined and we're not allowed to do that. Okay, irrational numbers, that's the numbers like the square root of 2, square root of 3, pi. All of these, if you put this in your calculator, you would see that the decimal for it goes on forever. There is no end to it. So all of those are irrational numbers. These cannot be expressed as a ratio of integers. Now, if I had something like the square root of 4, we know that the square root of 4 is in fact 2. So the square root of 4 would be a rational number. It's only these square roots that don't simplify that's going to be considered irrational. Okay, so one symbol that I want you to be familiar with is this double-backed R down here, and that's the symbol for set of all real numbers. So here's a Venn diagram representing real numbers. So this outer block here is the real numbers. Within the real numbers, we have the rational numbers and we have the irrationals. Okay, and within the rational numbers, we have integers, and then within the integers, we have the natural numbers. So all of those are subsets of the real numbers. And for those of you that may remember, your complex numbers are going to include all of this and also your imaginary numbers as well. Okay, so we mentioned earlier that terminating and repeating decimals are going to be considered your rational numbers. So if you have something like 0.5, 0.5 can be converted to a rational number, or is a rational number, and can be converted to the ratio of integers here. If you have one that's repeating, so like the 1/7 repeats on this, then that would be another example of a rational number that can be rewritten as a ratio of integers. And even this one, it has a big chunk that repeats, but it does have repetition, and so therefore it could be written as a fraction. But these, if you look down here, these are irrational numbers, the square root of 2 and pi. They go on forever. There's no repetition, so they cannot be written as a ratio of integers. If we take any of these and we were to chop it off at any point and list it as a rounded number, that number would be an approximation and it would not be an exact answer. So this would be an exact answer. This one would be exact, and this would be actually an approximation. Okay, so the approximation is this decimal that's been truncated here. The exact answer would be pi, or another example would be the square root of 2 would be an exact answer. And the decimal for it, no matter how many decimal places we write out, it's still going to be an approximation because the exact answer goes on forever. Okay, some of the properties of real numbers, we have the commutative property, and that just basically says for addition and multiplication, the order doesn't matter. We can add two numbers or multiply those two numbers and switch their order, and we're going to get the same thing. Obviously, that does not hold for subtraction, and it also does not hold for division. So those properties are not commutative. Okay, associative properties. With associative properties, that just means we can regroup, and they're going to be equivalent. So if I group A and B together, or I group B and C together, as long as I'm adding, then we're going to get equivalent answers. And also for multiplication, it's not going to hold again for subtraction and division. Okay, the distributive property, basically we can distribute from the front or we can distribute from the back is all this is saying. So if we look at this example here, we go through and we distribute, we're going to distribute the 2 to the x, and we'll have 2x, and then we'll distribute the 2 to the 3. So 2 times 3 is going to give us 6. So we have 2x plus 6. Here on this one, you may be familiar with FOIL, but basically what FOIL has us do is take this whole thing and distribute it to the x, and then take that and distribute it to the y. So we'll have a times x is going to give us ax, and then we're going to have a times y will give us ay, and then we'll have b times x will give us bx, and b times y will give us by. Okay. A couple other properties. The additive identity basically just says if we add 0 to something, then we're going to keep what we started with. Every real number has a negative. So if we add a number and it's negative, we're going to get 0. And subtraction, we know, basically undoes addition. So a minus b is the same thing as a plus a negative b. Okay, some of our properties of negatives, -1 times any number is going to change it to a negative. 2 negatives will give us a positive, and if we have a negative, whether it's on the first or the second term, it's going to be basically make that whole term be a negative, and you can see some examples here. Again, 2 negatives make a positive. If we distribute this negative through here, negative a, and then that would be negative b. Here, if we distribute, it would be negative a and positive b, which can be written as b minus a. Okay, so here are a few that I'd like for you to think about. So pause the video and think about what your answers to these would be, and then we will take a look at your response. Okay, looking at these, on the first one, you've got -3 and it's raised to an even power. So because this is an even power, I'd have -3 times -3, and that's going to give me a positive. 2 negatives make a positive. Here I have 3 negatives being multiplied together. So because this is odd, then my answer is going to be a negative. So anytime I have -a to an odd power, I'm going to end up with a negative, and -a to an even power, I'm going to end up with a positive. Okay, here's another example of distributing these negatives through. So if we distribute the negatives on this one, I'm going to have negative x minus 2, and down here I'm going to have negative x minus y, and then here a negative times a negative is going to give me a positive for my answer there. Okay, a couple other properties. The multiplicative identity means if I multiply this by 1, I'm not going to change the value of what I started with. And the multiplicative inverse says if I multiply it by 1 over a, then I'm going to end up with just 1. And we know division undoes multiplication. Okay. All right, so if we're multiplying fractions, you can use your calculator to multiply fractions, but I do want to briefly go over this. If you're multiplying, you just multiply straight across the numerators and straight across the denominators. So we have AC over BD, and you can kind of see that with the numbers here. Division, anytime you're dividing fractions, you're going to do keep, change, flip, or same, change, flip. So we keep this one the same. We change this to multiplication, and then we flip this fraction. And when we do, we end up with this as a multiplication problem. Okay, adding and subtracting is a little bit more complicated. We do have to have a common denominator in order to be able to add or subtract fractions. So if we have a common denominator, we just need to combine the numerators together. If we don't have a common denominator, we need to get one. So like on this example, we want to look and see what does both 5 and 7 go into. They both go into 35. So in order to have 35 here on the bottom, I'm going to have to multiply the numerator and the denominator by 7. And in order to have 35 here, I'm going to need to multiply the numerator and the denominator by 5. So I'm going to end up with 2 times 7, or 7 times 2, plus 3 times 5 over 35, and I get 29 over 35. Okay, if we look at this property just says if we've got these common factors, we can cancel those out, and we'll have a over b. And here, if we have two fractions equal to each other, then we can cross multiply. And cross multiplying, we'll do a times d and get AD, and then b times c, and we'll get BC. So this is a common property that we will use quite a bit. Okay, here's a few examples. If we multiply straight across here, 2 times 4 will give me 8, 3 times 7 will give me 21. Always look and see if your fraction can be reduced. If it can, then you need to reduce that. If you're putting this in your calculator, if you have an older calculator, be sure that you put parentheses around your fractions. If you have the newer ones, they automatically kind of set the fractions up for you, and it'll work pretty well with that. Here we have a division problem, so we want to do keep, change it to multiplication, and then flip the second one, and then we'll just multiply straight across. We do have these common factors that we can cancel out, and we'll end up with the 2/5. Here we're asked to add, and we do have common denominators, so we'll just add the numerators and get 7/5. Notice we don't do anything with the denominators, we keep those the same. Okay, when we come down, see. Okay, when we come down here, we don't have common denominators, but if we look at 3 and 5, 3 and 5 both go into 15. So our least common denominator is going to be 15. And if I need this to be 15 on the bottom, then I'm going to have to multiply by 5. And if I need this one to be 15 on the bottom, then I need to multiply by 3. So I'll get 5 times 2 is 10, 4 times 3 is 12, and so I'll end up with 22/5 for my answer on this one. Okay, so this one's a little bit more complicated, and I want to go through the process when it is more complicated, mostly not because you can't put this in your calculator and get an answer, but because the process is going to be transferable to when we're looking at these being algebraic expressions. So if you understand the process, it will be helpful for later on. So if we look at 36, we're going to do the prime factorization of both of these. So if I take 36 and I say what goes into 36, 6 and 6 go into 36, I'll keep splitting these up using until I have all prime factors. So 2 is a prime factor and 3 is a prime factor. So I have 2 to the, I've got 1, 2, so 2 to the second power, and then 3 to the 1, 2, 3 to the second power. If I do the same thing for 120, you don't necessarily have to start out with 12 and 10. There's a lot of other factors that would work to go into 120. You'll still end up at the same place. So 12 and 10, if I break this down, it would go in 4 and 3. 10 would be 5 and 2. 4 is not prime, and so I need to continue to break that down further to 2 and 2. So when I look at these, I've got 1, 2, 3 2s, and that's where this 3 comes from. And then I have another 3 and another 5. Okay, so I'm ready to go with this from here. If I look and find out, my least common denominator is going to be, I'm going to look at all of my bases, and I'm going to look at those to the highest power. Okay, so if I do that, I can see that I have a base of 2. If I'm comparing this to this, have a base of 2, a base of 3, and a base of 5. So I'm going to put those here, 2, 3, and 5. Okay, when I look at my 2's, this one's to the second power and this one's to the third power. I want to take the highest. So I'm going to do 2 to the third power. And then on the 3's, I've got 3 to the first and 3 to the second. So my highest power is this 2. and that's where this 2 is going to come from. I only have the 1, 5, so it's going to be here. Okay, so if I look at this, this is going to be my least common denominator. If I multiply all that out, it's going to be 360. So if I've got 360 and I look at what I have here to begin with, to go from 36 to 360, I need to multiply the numerator and the denominator by 10, and that's where these 10s come from. To go from 120 to 360, I need to multiply it by 3, and that's where these 3's come from. Okay, so multiply the numerator, multiply this numerator, I'll get 50 and 21, and then I have 360 in the denominators of both, combine them together, and this is going to be my answer. Okay, complex fractions is another important thing to be able to do. And again, you could put this in your calculator, but at some point we're going to have x's and y's in here, so it's important to understand the process. I would say look at it as 3 different problems. Do this problem first, the numerator, the denominator, and then combine them both together. Okay, so if I'm looking at this numerator, the common denominator of these 2 fractions would need to be 10. Okay, so in looking at that, this one needs to be multiplied by 2, and this needs to be multiplied by 5 in order to have 10 in the denominator. So I'll do 2 over 2 and 5 over 5, which will give me 4 plus 5 over a common denominator of 10, and I'll get 9/10. If I come and look at this denominator here, if I've got 10 and I've got 15, both of those go into 30. So 30 is going to be my least common denominator. If I look here to get 30 in the denominator, I need to multiply by 3. So I'll do the numerator and denominator by 3. Here I'll do the numerator and denominator by 2 to get 30 in the denominator. Multiply across and I'll have 3 plus 6 is going to give me 9. And then I'll have 30 in the denominator, so 9/30. So I've done the first problem, okay? I've got the first problem, and then I've got the second problem, and now I'm on to the third problem. So the third problem is where I take the answer to the numerator, the answer to the denominator, set it up like this, which is just another way to write a fraction. So I'll do keep this, change division to multiplication, and then flip the denominator. I've got common factors, so those are going to cancel. So 30 over 10 is going to give me 3 for my answer. Okay, a couple other things to wrap this section up here. The real number line, you should be able to place anything along the number line here. I think that's pretty self-explanatory. Any real number could be represented on the number line. All right, we know that we have our inequality symbols. Anything to the left of this is going to be less than. Anything to the right is going to be greater than. Okay, so set notation is something I want to talk about. We've got this symbol here, which means it's an element of or it's a member of. So this would be A is an element of the set S. This would be B is not an element of the set S. Okay, so Z represents the symbol for integers. So like pi, we said, was an irrational number. It would not be in the integers, so it would be not an element of the integers. Okay. This is set notation to represent, like, if A is the set of all positive integers less than 7, then we would have this listing here to represent that. Okay, so we can write it in set builder notation too. So this would be A is the set of all x such that this vertical line is read as such that x is an integer between 0 and 7. Okay, so we'll talk also in this section about unions and intersection. Union is kind of the U-like symbol. Basically, it consists of all elements that are in S or T. We don't list anything twice. We just list everything once. The intersection is the overlap part. So in order for it to be in the intersection, it has to be in S and also in T. So it's the common part of S and T. And then occasionally we have the empty set, which is like the circle with the slash through it, that tells us that there is no element, that it contains no element. Okay, if we look at these examples here, we've got S union T. So if I'm going to do S union T, I need to write everything in S. So I'm going to have 1, 2, 3, 4, 5, and then anything additional in T, so 6 and 7. Okay, so that would be S union T. If I do S intersect T, then it has to be in both S and also in T. So if I look, 4 is in S and T and 5 is in S and T. So this one would be the set that contains both 4 and 5. And then if we want to look at the intersection of S and V, we can see that nothing overlaps. So we would have the empty set for that one. Okay, some notation. In WebAssign, you are asked to give your answers in interval notation. With interval notation, basically if you have an inequality without the line under it, that's going to be considered an open interval, and you're going to use parentheses to represent those. And if it does have the line underneath it as down here, then you're going to represent those with brackets. Okay, so this would be the notation to represent the interval from A to B, not including A or B. This is the interval from A to B that does actually include both A and B. So here's some examples. This is just showing on the number line how it's shaded in from A to B. So if it has parentheses, these will be represented with open circles. And if it has brackets, those are going to be the closed in circles, solid circles. You can have all different combinations of these. You can have a closed dot on one end and an open circle on the other end, and vice versa. Or you can have it start at one place and go all the way to the other. So that if this is going to infinity over here, then our notation would be from A to infinity. Infinity always gets an open parentheses. Infinity will never have a bracket, so it should always be a parenthesis. This one has a closed circle, so it's going to be a bracket. This one's an open circle, and this is going to negative infinity. It's always read from left to right, so we would put negative infinity first and then the B, and here also negative infinity and then the B. And if you color in the entire number line, then that's going to be your set of all real numbers, which we represent as negative infinity to positive infinity. Okay, so we'll combine unions and intersections of these different intervals here. The first one is looking at the intersection. The second one's looking at the union. Okay, so if we take the first one and we graph from 1 to 3, these are parentheses, so these are going to have open circles, meaning it doesn't include 1 and it doesn't include 3. If I look at from 2 to 7, those have brackets, so it does include those. So if we're wanting the intersection, that's kind of the overlap here. Okay, if we look, this is going to be this part in here. Okay, so the part from 2 to 3 is the overlapped part. The hard part becomes, do we include the 2 or do we include the 3? So for it to be an intersection, it has to be in this set and also in this set. So if we take the number 2 and look at it, 2 is included up here because it's part of this solid line. It's also included here because it's a solid dot, so we would include it as part of our final answer. If we look at 3, 3 is not included here, but it is included here. But to be in the intersection, it would need to be in both. So this would be an open circle for 3. And we would shade in between. So as far as your answer, all of this is just preliminary work up here. Your answer would be this, and the graph of your answer would be this. Okay, so just clear that while you may do these preliminary graphs, your final graph and your final answer is going to look something like this. Okay, if we change this and we do the union of these same two sets, the union is everything that's included. Okay, so here we're actually going to go from 1 all the way out to 7, because everything from 1 to 7 is included. And with union, it doesn't have to be included in both, just in one. So if we look here at the number 1, it's actually included in neither set, so it's going to get an open circle. But if we look at the number 7, it is included here, so it's going to get a closed circle. So for the union, it just has to be in one of the two sets. For intersection, it has to be in both of the sets. Okay, so here's one to practice on. You can, if you want to kind of cover this part up and practice, that would be fine. If we look at going through the same thing, you've got this kind of practice graph where I combine the two together. For the union, it's going to be everything, so it's going to be from -2 to 9. And then for the intersection, it's going to be this overlapped part in here from 0 to 5. 5 is included in both, so it would get a darkened circle. 0 is included in only one, so it would get an open circle there. This is how I'd write the interval notation for both of those. Okay, so the final thing I want to cover in this section is talking about absolute values. So absolute value is basically just the positive distance something is from 0. Okay, so the absolute value of 3 we know would be 3. The absolute value of -3 is also 3. Absolute value of 0 is 0. And I'm not even going to get into that. These are some absolute value rules. You're welcome to take a further look at them, but they're not something that we're going to focus on all that much. I want to look at this one example here. If you want to find the distance from A to B, that of course is the same as the distance from B to A, and we write that as the distance from A to B. And our formula for finding that, if we're talking about on a number line, is the absolute value of B minus A. So if we look at this example, the distance between the numbers -8 and 2, just quickly, if we look at this, if we're at -8 and we're over here at 2, then we can see that there's 8 units here and there's 2 units here. So our distance is going to have to be 10 units. So just visually, we already kind of know what the answer is going to have to be. But if we look at this, we've got the absolute value of B minus A. So that's going to give me the 2 minus a -8. So that would be the same thing as 2 plus 8, which will give me the absolute value of 10. And so that's going to be 10. Okay, so you can see geometrically what this looks like, but then you can also see algebraically how we arrive at that. Okay, so that takes us to the end of section 1.